going on, guys? Let's do this problems right here. So the first question is asking a simple harmonic oscillator has an amplitude of 3.5 centimeter and a maximum speed of 26.0 centimeter per second. What is its speed when displacement is 1.75 centimeter? Let's see how we can calculate this one. So first of all, we have maximum speed right here. So we know that V is at maximum, V max is equal to A omega, and that is provided 26.0 centimeter per second. So we have V max and then displacement, and we have amplitude. So amplitude is equal to 3.5 centimeter, and we have displacement x is equal to 1.75 centimeter, and they are asking for the velocity. Velocity equation is v is equal to minus a omega sine omega t. This a omega can be replaced by this one, but omega t, we had to do something about this, right? So let's find omega t using displacement equation. So we can use the displacement equation. X is equal to a cos omega t, right? So if I switch this around, this is going to be omega t is going to be equal to x over a, so cos inverse x over a. So cos inverse x value is 1.75 divided by 3.5 centimeter, and if you calculate this value, this one comes out to be 1.047 radians. So we have omega t right now. All we have to do is simply substitute all the values. So we have minus a omega, that is 26. So 26 multiplied by this one, this is 1.047 radians. 1.047 radians. This is centimeter per second, and that's all. And this is sine omega t. Okay, I had to put sine in front of it. Okay, this is sine omega t, right? Sine 1.047, right? If you calculate this one comes out to be minus 22.5 centimeter per second. So this gives us minus 22.5 centimeter per second, and we can say magnitude of this one is equal to 22.5 centimeter per second. And if you look at the answer, we have D, that gives the same answer. So the answer for this one is D. And let's look at the next one. Next question is asking a restoring force of magnitude F acts on a system with displacement of magnitude of x. In which of the following cases will the system undergo simple harmonic motion? Okay, we have F directly proportional to root x, x square, x sine x, 1 over x, and we know that F is equal to minus kx, and if you see F is directly proportional to x, so we can say C is the answer right here. So C is the answer for this question. And this next question is asking which of the following graph describes a simple harmonic motion with amplitude 2 centimeter and angular frequency 2.0 radians per second. Let's see. First of all, let's figure out all the graph that has 2 centimeter amplitude. This one doesn't have 2 centimeter amplitude. This one have 2 centimeter amplitude, and this one also have 2 centimeter amplitude. This one, yeah, this one also have 2 centimeter, and this one doesn't have because it's 1, right? So this one doesn't have. So 3 possibilities amplitude. And now we have to find the omega. So they have given the angular frequency, that's omega, right? Omega is equal to 2 pi over t or 2 pi f. But in this case, 2 pi over t is very useful because we can find the period of the waves easily. Here, the period of the wave is basically the time required for the wavelength to travel one wavelength, like the time required for a one wavelength to travel. So here, if you look at this one here, if I start here and if I end here, that's 2 seconds. And for this one, if I start here and end here, this is 3 seconds. And for this one, this is like 3 2. Oh, this is too big. Now this one is actually one. This is half of the wavelength. So for the half of the wavelength, it takes 3 to 9, 6 seconds. So for the full wavelength, it's going to be 12 seconds. So if I divide 2.5 by which number, give me 2. That's the question right here. We know 5 is around 3, right? Around 3.1, something like that. And if I have to, so the 2 times 3 is going to be 6. 6 divided by which value gives us 2, around the value around 2. 3, right? So we have to look at the period that has 3 seconds. And in this case, if you look at the C, that has 3 seconds, and that is the answer for this question. And that's how it's done. I hope you guys like this video. See you next time.